So good afternoon, everyone. I am Baraa from Leibniz University, Hannover. First, I want to extend my thanks to the organizers and for this excellent workshop and for all the speakers for their insightful presentations. It was really amazing for me. So I am excited today to share our works, theoretical works on pathways to ultra-cold ground state triatomic molecules NaK2. Okay, so let's have an overview. We propose two theoretical pathways. The first one is to form weakly bound ground state using microwave field, red detuned from rotational excitation of the diatom by stimulated photon radiation. So the next pathway, the next pathway is built on the experiment of Cao et al., the Ban group, where they have already observed photo association signals starting from collisional state of the ground state sodium potassium and the ground state potassium. They have used Feshbach optimized photo association to observe those deeply bound excited state in the third doublet A prime. And they have used a laser light of 1558 nanometer. So what we are proposing is a stirrup scheme to stimulate the decay, to stimulate decaying to the deeply bound ground state NaK2 in the first doublet A prime. Okay, so what is the methodology we used to approach those two proposals? First, for the weakly bound ground state, we have used ab initio calculations for the long-range potential energy surface, and we have approximated the short range as Leonard short potential. Then we have used the coupled channels method, very simplified model, to calculate the eigenvalues and the eigenfunctions. Using a perturbative approach, we have estimated the association rate for forming weakly bound ground state. And for the stirrup scheme, we have calculated the short-range potential energy surface. And we have also calculated the potential energy surface for the excited state, the third doublet A prime, and for the ground state, the first doublet A prime. And we have calculated also the transition dipole moment surface between the two electronic excited states. So then we have used a discrete variable representation method to calculate raw vibrational energy levels and the raw vibrational wave functions. After that, since we have already the transition dipole moment surfaces, we have calculated the line strengths between for the raw vibrational transitions from the excited state manifold toward the absolute deeply bound ground state. Okay, fine. Now we can start with the weakly bound ground state. Okay, we call this process electric microwave association. Why electric? Why electric? Because this process relies on the interaction between the electric component of the microwave field with the dipole moment of the diatom. And since and it works only for dipolar diatomic molecules. And since NaK has relatively large dipole moment to 2.7 dBi, it can, we propose to start with a scattering state where sodium, potassium in the ground state and potassium in the ground state. Now we apply a microwave field. With that microwave field, one can drive transition down below that channel to form loosely bound state in the electronic ground state of the trimer by photon emission, or by photon absorption, one can drive transition to pre-dissociating triatomic state, which is below the first rotationally excited state of the diatom. So this is the idea. And I have told you before that we have used couple channels calculations, but very simplified model. We didn't include the fine or hyperfine structure of the atom or the diatom. Our basis vectors consist of two angular momenta, the rotational angular momentum of the diatom, the relative angular momentum, small l, and those two angular momenta, they coupled to form the total angular momentum, total J. This is our basis vectors with 13 channels. We have approach conversions. Okay. So this is the results of the couple chance calculations. What you see here is the association rate, the microwave photo association rate, as a function of the microwave frequency in gigahertz. This vertical arrow indicates the position of the first rotationally excited state of the diatom. And those with the negative index are weakly bound states below the entrance channel, and those with positive index are pre-dissociating triatomic states. And what does it mean, pre-dissociating? It means that it can dissociate again to the open channel J equals 0, L equals 1. This horizontal dashed line represents typical loss rate from the trap. And as you can see, those association rates are much bigger, higher than a typical loss rate. That means that we might be absorb those resonances. And we have, done these calculations at, so the intensity of the microwave here, it's not fixed. We have varied this microwave intensity because I have told you before that it's a perturbative regime. We don't want to perturb the energy levels of the diatom. That's why we consider that the omega, the Rabi frequency, is one order of magnitude less than the detuning from the rotationally excited states. So once you are close to the rotationally excited state of the diatom, one has to decrease the microwave intensity. So as you can see, with about 10 to 100 watts per centimeter squared, one could absorb those resonances. And I should note that we are not predicting positions of those resonances. We are only predicting the density of states. And we are just guiding the experimentalist that please do that. You might absorb those signals. And those association rates are calculated at temperature of 200 nanokelvin, considering density of sodium potassium 10 to the power 12 per centimeter cubic, per cubic centimeter. Okay, this is just just cartoon how it works, that you have a cloud of potassium atom, you shine a microwave field. Once the microwave field is red detuned from the rotationally excited state, you can form those weakly bound trimer. Now we move to the second proposal, where we have calculated the potential energy surface for the excited state and for the ground state. So this is just energy diagram for the triatomic system, where on the right side, those are three atoms, 2 potassium atoms and sodium atom. Here to the next, we have sodium potassium plus potassium, and next we have sodium plus diatomic potassium. And on the left, we have the electronic state for the trimer described in CS symmetry. The red dashed line, this is the laser wavelength used in the band group. And the green dashed arrow, it's only just proposal to reach the same electronically excited state, but not starting from sodium potassium plus potassium, starting from diatomic potassium in the ground state plus sodium in the ground state. This blue arrow, this is our estimation for the spacing, which is around 1198 nanometer with 15 nanometer uncertainty because of our ab initio calculations. So since we have studied the potential energy surfaces for the ground state and for the excited states, we have identified three geometries. One that has obtuse isosceles triangle, and one that has acute isosceles triangle. The one with the obtuse isosceles triangle represent a local minimum on the full potential energy surface of the ground state, and also for the excited state third diplet A prime. The one with the acute isosceles triangle represent a saddle point on that surface, and the distorted geometry is a global minimum on that surface. I will just go faster because I run over time. So this is the result of our DVR calculations, the 0-point energy located at 101 wave number above the global minimum of the ground state. The one which is the vibrational level localized around the local minimum is located around 336 wave number. Now we will see the vibrational wave function. This is for, which is localized around the ground state. This is localized around the local minimum in Jacobi coordinates. And what is interesting, this is the interesting point, that the observed resonances, this is the wave function for the observed resonances, our estimation, our calculation. And you see that this vibrational wave function, it can occupy both regions, the region which is around the global and the one around the local. It's like a superposition of two vibrational wave functions. So it has high Frank-Condon factors with both the one which is around the global and the one around the local. Yes, and we have then estimated the line strengths. I will go faster. The important point that the line strength is around 10 to the minus 2 dBi squared near local minimum, and 1 order of magnitude less near global minimum. But this is experimentally, hopefully, will be observed. With that, I come to acknowledge my supervisor, my colleagues, Zilke Osbelkaus, Ibarat Timan, Leon Karpa from Leibniz University, Hannover, and Olivier Delieu from Laboratoire Aimé Coton, and thanks for your attention.
Thank you very much for this nice talk. Questions? Dejan?
You know, the factor resonances between NaK and K and the potassium were not fully understood.
Yes, it's not fully understood.
Have you tried to use your potential to model that?
We are just guiding the experimentalist, so there is no way
No,
to
no, I mean,
progress.
They already observed the fiber resonance between NaK and potassium, right?
Yes, the
From the
resonances.
USTC group. But now you have the potential. Can you try to somehow understand that?
Sorry, could you please just reformulate the question?
Yeah, I mean, the USTC resonances were not fully understood, right?
Exactly, not fully understood. We are trying to understand that with these sub-initio calculations. We are not making predictions. We are just trying to understand. But thank you very much for your question.
Hi, Baraa. Nice talk. Did you consider the effect of collisions when you photoassociate for the trimers NaK and K? Did you look at the effect of collisions because they are maybe sticky collisions or?
No, I didn't do dynamical calculations.
So, but do you think it will affect the efficiency of this photoassociation or?
Of
to some
course,
extent?
I think it will affect.
Okay.
Yeah. Thank you very much.
Dima?
So you showed the DVR energy levels. And you mentioned a few things about a mole, but I'm just wondering, you didn't show the Hamiltonian or anything. So is it one-dimensional calculation? Or how
No,
many-
it's a three-dimensional. I calculate the potential energy surface in 3 dimensions.
Aha. How about conical intersections and all the stuff that we now know occurs for this kind of atom molecule systems? Of course, it was not included, but then your levels do depend. Do you have a short range cutoff, or how did you do that? How did you do the energy, the calculation of energy levels? Because they do depend on the short range and all the entire properties of the potential surface that you didn't calculate.
Okay, a very good question. Thank you. So for the stirrup process, I calculated the short range potential energy surface. Yes, but for the microwave association, we are just considering that the long range dominate the process. So we are treating the short range as boundary conditions.
Okay.
Yeah.
Okay, that's the answer. Okay. Thank you.
Yes.
Okay, I think we should stop there and thank Baraa and all the other speakers of this session.
Thank you.